Så det giver mening for mig, fordi Windows og Linux er jo forskellige.
Ja.
Så derfor har vi det bare som en svat linje. Ja. Præcis så. Og så det er virkelig noget struktureret, vi er næsten færdige med at bare løse det problem, at vi har en fejl for det inline.
Okay.
Og så skal jeg mathe.
Anyone who knows what is the room number here? Yeah, please check, because I'll send out.
Men det er da meget godt. Hvis vi så, altså, hvis der næsten bare skal skrives tekst der, og der skal. Okay, so we are working on a project about kernel selection in Gaussian processes. And just to recap the problem, a Gaussian process is a stochastic process where we assume that the signal we are trying to model comes from a multivariate Norman distribution with some mean and some kernel matrix. And then the overall problem is how to choose the optimal kernel or combination of kernels. So our solution is to choose some large kernel form, and specifically we have worked with something like that is a product of linear exponentials and periodic kernels, and also sums of those. And then our wish was to sample both theta, which determines if a kernel should be included in the kernel form or not, and the kernel parameters in span.
Yeah, so the prior that we chose on these thetas that are really determining, like Nick said, if some kernel form is in the exact kernel or not. So I mean, if all thetas are 1, you can see from the kernel that it's a very flexible model and everything is in it. So we tried to penalize these thetas. So we put this Bernoulli distribution on all thetas that is governed by this lambda over here. So I mean, all thetas are in the prior independent of each other. So we can represent this prior as this matrix of thetas, where in the rows we have if they're in each sum, and in the columns if they're in each product. Now this gives also, I mean, these Gaussian parameters that are in the kernels are then should have a sparse representation. So this means that possibly we have to parameterize the usual parameterizations of kernel functions. Yeah. So the first thing we tried was to do everything in Stan at once. But I mean, it was a bad idea because all these convergence diagnostics and such, they don't really handle these what we call discrete variables very well. I mean, it's not, we couldn't really read anything from it, and also it takes very, very long time. So we tried something else.
Yeah, so our second method is more like a brute force method. So instead of like having theta as parameters, we feed it in, and then we just evaluate every combination of theta we can come up with. And if we have like I different kernels and j different number of each kernel form, then we would have to evaluate 2 to ij GPs in Stan. Lucky for us, because of the way we represent it, actually many of these models are the same, so at least we can reduce the number of models we had to evaluate in Stan. And this was a lot more promising. We got okay n effectives, and our hat values are also okay, and the diagnostics also show okay convergence. So yeah.
Maybe we should say that we instead first evaluate every single data representation, and then when we sample again, we subsample from all these samples that we have. So it's effectively like a new state space we run our markup chain on after to get our prior. so up in the right top corner, you see something that at least we like, because on the x-axis it's a lambda. So the higher we choose lambda, the more simple models we get, and the smaller, the more flexible models we get. And actually, we're quite pleased that we see this tendency that there is some minimum. And the error that we're minimizing here is on the test set, 10 points on this synthetic data set that we created. And it's the square loss we're minimizing. And the last two here is for lambda equal to 0.05. You see it has quite a narrower band around here. But I mean, these plots are not the best representations of this. So probably in the report we will draw full GPs that runs through it. This is like a linear correlation. And over here we have quite wider band, meaning and this is similar model. So yeah, because this takes a long time, we are still running it on this manual lower data set, which we see here, and probably, or we are hoping at least, that we'll see something with a periodic kernel and linear kernel in the end. But yeah, we're still waiting for our computer to finish these calculations. Yeah, so that's also the conclusion that you probably shouldn't use Stan for this GPU question. I mean, GPU question in general is quite expensive computationally. Yeah.
Can you go back to the subsampling thing? Explain that again.
Yeah, so basically what we are sampling is these posteriors from this distribution where we condition on theta.
Mm-hmm.
And then basically we just sum these out later on theta. So like we get this state space where we sample from Stan, and then we go in all models and make a macro change on this state space, and then we add our file there.
Okay.
What is the argument for actually starting to choose different kernels? Can you just use all of them and then compare the final results with those?
So you mean like adding all kernels to the form, or?
Yeah, but also just choosing every single kernel and running the kernel.
Oh.
Wouldn't that improve the result?
Yeah, maybe. But I mean, also an effect of this is that you don't have to choose one exception kernel. I mean, you can have some variety and say, hey, maybe there are two kernels that are both actually represented.
All right.
And when you say that GPs don't do GPs in Stan, so there are already some cases where they work, but they are really cases where, like hierarchical models, where each GP observes only small number of observations. But then it's with, if one GP is conditioned on many observations, yes, then Stan is really slow. And even if it's getting faster, of course, software which is specialized for Gaussian processes will be faster.
Yeah, so we have to create all of these kernels ourselves within Stan, so it's a lot of for loops that we have to run through every time.
Okay, thank you. Who's next?
Next or there. Yeah.
You need to rush. Just jump.
Yeah, just jump. Move the chair.
We want to see fighting up there.
Yeah.
Bribe of the teachers. You know.
Okay. Hello. We are Jakob Rasmussen and Mads, and we are from biomedical engineering, all PhD students. And our project is related to a question which was stated in a competition on a conference for wearable devices, where they stated a question: if patients admitted to the intensive care unit on the weekend are more likely to die compared to those admitted on a weekday. And to answer the question, we have a bunch of data, all taken from this big database, where we have data from a New York-based hospital from 11 years, 12 years. And we have roughly 20,000 patients. After we have cleaned up some data, the cleanup consists of removing unreliable measurements and such. And yeah, data is extracted from digital systems. So the data is basically patient demographics, and it's things you measure normally in an intensive care unit on the first day of admissions. So you have a bunch of scoring systems ranging from 0 to 100, let's say, for some of them. And the higher they are, the more likely, they say at least, the patients are to die. So we train different models. We compare, first of all, is the patient more likely to die on a weekend compared to a weekday. We also try to take each day individually. We try and take full linear model where we want to predict the patient coming into the ICU, is he going to die based on some of the parameters we can measure. Then we describe the correlation of the variables, and if we can remove some of them in order to get high performance still. So first of all, we answer the question. We see that on a weekday, a patient has a risk of dying of roughly 8.6%. It's way higher on the weekend, and the odds ratio is as we see. So that's it. No, we also take day by day, just to see maybe it's worse to get admitted on a Wednesday compared to a Monday. So we see that there are tendencies maybe that the later you are in the week, the higher the risk of dying is. But we see at least for the weekend, Saturday and Sunday, it's specifically problematic to be admitted. And we take the odds ratios between all the days, and we see that indeed it's worse to be admitted in the weekends compared to the weekdays. But there's also tendencies that Thursday and Friday might be worse than the beginning of the week.
Yes. And then we try to take some of the parameters that we have in this data set and put it into a linear model and train. So with the previous analysis, we saw that we can sort of see that if we split the data into like weekdays and weekends, then we can see the biggest difference. And so we have trained a linear model on the data from the weeks and the linear model on the data from the weekends to sort of see how some of these parameters they interact with each other. So we have what we have put into the model is some specific patient data like gender, age, how long they have been submitted to the ICU, that's the last ICU, weight, height, and then the rest of these parameters are sort of some of these clinical scores that should predict how bad the patient has it at a certain time, and this is at admission time. We see some of the scores have like a positive influence on the model, whereas some have a negative. And we some of it is a little weird. So we think that they all had a positive influence on the risk of dying, but some of them is very highly correlated. So there might be some combination of these scales that we can see in like just one use of each scale. So if we compare from week to weekend, then we see that of course we have a lot less data for the weekends. So we get more uncertainties in these
All right. It was of interest to look at the correlation between the input variables, and as you can see, the block in the middle, from oasis to mlots, are very correlated, and it may be of interest to look at a subset of variables because they provide no additional information. And all these from oasis to mlots are also like the sort of calculated measures, all coming from some of the other combinations of variables. So yeah, thanks. I tried to. Oh, sorry. We tried. There is ego. We tried to look at specifically the block in the middle, these 7 variables that were very correlated, and look at the predictive densities of models, including all of them, and simply removing all of them. So this plot shows the difference from the complete model, including all the variables, to none of these 7 variables. And we did this to sort of pick out which of these variables that are very correlated might contribute the best to the predictive density of the model. And so from here to here, these are only including one of the 7 variables. So for example, it's the model containing all but the 6 variables apart from oasis. And these are the complete model, but for example, APS triple I. So what we can see from this is that the variable that supports the model the best seems to be these 2, because it has only including this and leaving the rest of these out, gets the closest to the complete model, and also leaving this one out in the sort of reversed case where we include everything but these also reduces the predictive capabilities of the model. So it seems like it would make sense to include at least this one and maybe leave some of the others out. I should say that this is sort of a subset of a complete model where you include all the variables and look at them in a complete sense. And there was an R script for it to do it very easily, but we did it in Python. So we still need to make the complete analysis, but we'll probably do it for the report. So this was just a sort of a subsample of the illustration.
Yes, we found a lot of interesting conclusions. Of course, there are more things to check. Firstly, we thought of that we know that we have a bunch of different ICUs that we compare from. You see some of them here: coronary, cardiac, cardiac, etc. We have about approximately 8, I think. Could be tested if one is worse than the other. For example, on the coronary care unit, is it in that specific unit worse to be a weekday compared to a weekend? How is the care in that unit for the others? We also have some different admission criteria for patients. We have some that are cost of elective surgery, some are emergency, some are urgent. And we can test if there are differences between the patient groups. And finally, we talked about that it could be interesting to evaluate the models on unseen data. Here we have so much data, so we easily leave something out and test the predictive performance of the linear models, if we can actually predict correctly if a patient is going to die. That was it.
I have a couple of questions. Very interesting. If you go back to the first where you summarize the data. Yeah. No. Yeah.
I'll summarize the.
Yeah. The histogram. This one's. What is it you actually show?
That is the probability of dying. Simply. If you are admitted on a given day. So we have the number of patients admitted on each day, and we have how many died actually.
Okay.
So it's very simple models.
Okay, so you actually kind of, okay, so that was my question. How can you actually get a distribution? That's because you look per day. Okay,
Yes.
okay. Then I heard you say that you actually built one model for each weekday to kind of find the
Not
kind of
linear
the
models.
Not in the linear order.
No. Then we took in two groups, week and weekend.
yeah, okay.
You can also do it individually.
Yeah, but you built, I mean, you could also treat the day as a covariate
Exactly.
and then build one model.
Yeah.
So in order to estimate the treatment effect, what do you think is best? To build one model where you include the treatment as covariate, or build separate models for each treatment? Oh, here the treatment is the weekday. It's a very hard question, actually. So
I mean, so what we ended up, we have also looked at building a hierarchical model where we sort of look at all the data and then have the weekdays in. But we've had troubles optimizing that in Stan, so it takes a long time. We have 35,000 or something data on 35 something thousand patients, so it takes a long time to run in the hierarchical model because we haven't been able to optimize it. But we have it running.
yeah. So my intuition before was that actually it's better to build one model, because then you kind of infer the parameters on all the data. But there was a recent paper I saw where they actually argued the other way around, and that's, I think the argument, as far as I understood it, is that if there is some kind of confounder that actually kind of that kind of the state of the patient both decides what treatment you give and the outcome, then it's actually better to kind of divide the two. I don't know if you get the argument. I mean, I barely get it. Which leads me to the last question. If you take this kind of heat map you made, could there be some kind of confounder here in the data?
What do you mean?
If I'm not feeling very, very bad, but I'm still feeling kind of bad, I know, okay, I have to go to the hospital at some point, then I might say, okay, I can actually wait until, if it's Sunday, I say I can actually wait until tomorrow. And that could be then the people who are not as bad. I mean, the people who are not as ill will be kind of the population of Mondays, whereas people who come on Sundays, they say, okay, really, I'm going to die, I have to go to the hospital now, right?
But
Can you
ICU units, so this intensive care units. So
Where you go after surgery.
after surgery, or if you're in a car accident or something like that.
Okay.
You are severely ill when you come to these units.
Yeah, but not necessarily, like also elective surgery, which is done during the weekdays, you go to the intensive care unit. So you might have a lot of patients that have just done elective, pretty non-complicated surgery, and they go there, they don't die.
Okay.
And the ones going on the weekend, they are just because they're urgently. So I would say that's a pretty big confounder.
Yeah. And some have tested, I know that to test for the different patient groups, how are you more likely to die on the weekends compared to the weekdays, and it showed that patients having an elective surgery on a weekend was more likely to die than those on the weekdays. And patients are not getting elective surgeries on the weekends. So there are some errors in the data set.
There are more question comments here?
It was just of interest. Do you think, is it because in the weekend people get shit drunk and get hurt, or is it because that in the weekend the intensive care, because people get shit drunk and hurt, then it's overfilled? Or what do you think?
We actually discussed that.
Yeah,
It'd be quite interesting to have like a sample of young people compared to
Exactly.
people not that drunk in the weekends.
Yeah.
But there's also been a Danish PhD just recently who showed the same thing for a Danish hospital, where at least their theory is that in the weekends the doctors on call are usually not the most competent ones, and sort of you're also usually in like it's split in two teams in the hospital. You have those that usually take like weekends, or you're on roll, so in teams. So it could also be that the transfer of information from weekend to weekdays are less, and you sort of don't feel as connected to a patient like that. When you show up on Monday and there's been 3 new patients, then you sort of want to take care of the ones that you admitted Thursday or Friday, or whatever. That's, at least that's what they are looking at the hospital in Denmark.
So in UK, when this result was reported, then one of the first hypotheses was that hospitals are understaffed during weekends. But it seems that there's a lot of these guesses for the reason without looking at the data. So. And then I would suspect that although like, of course these can be also reasons, the understaffing and younger doctors and so on, but I would expect more on who is coming in on certain days.
Yeah, and that's also why we would like to sort of get predictive values out of our models, so that we can see if the data that we actually have is predictive of why they die weekdays or weekends, or if we have to look at other data to get a model that can actually predict whether a patient will die weekday or weekend.
Then can you show whether you have the marginal posterior, this one? So here I wanted to mention that whenever you see this kind of plot where some of the variables have much wider distribution, it's likely that it's because of the strong correlations.
Yeah.
So now the weight, height, and body mass index. So if you would plot joint distribution, like the 2-dimensional joint distribution for these, it's quite likely that it could be narrow with strong correlation. So it's just kind of the, remember always then in those cases to suspect collinearity if you see some variables have much wider distribution than others.
Thank you. Very interesting. how to use a modern MacBook
Yeah.
to give presentations.
Or how to use monitors. Yeah.
But it's also this
Yeah.
so it's try to
Yeah.
Okay, yeah, okay, so you can start talking and then I can play with this. Yeah, I mean, I think you should start the presentation.
Yeah, okay.
Do you want me to go on the record?
And I'll do it. Okay, but yeah, you go on and give it like an introduction to what's the point of the project.
Yeah. You can say our names. So I'm Maximilian. This is Laura, and this is Laura. And we've been working with a huge data set given from a company producing isopropyl alcohol. So, and they really love monitoring like all different variables in the process. So we got hundreds of variables, and for every 5 minutes in 1.5 years, and then we try to get something clear out of that. Yeah. Now what else?
So as Mike already said, the data is from a factory where they produce isopropyl alcohol, and of course the overall goal is always to maximize production. And for that they have a lot of variables, and they can set exactly 2 of them, or 2 are the ones that they actually set. Most of the process is automatic, but they still need the human operator in there to set some of the variables that they can't find any specific rules for how to set them. So our first goal was to identify from the process that we got, so from the 500 variables plus the 2 operator variables, what operator was currently in running the process, because that data is anonymized, and then from that derive some rules that the most successful operator would be using. Right now we finished the first part of our project, which would be so we start with first identifying the shifts, because there are shifts of different lengths over each day. And from that we first want to predict the overall performance over the entire shift based on the data set of the operator variables. So we had to start with first pre-processing our data in some way. We started out with the data, and we first had to clean out some shifts where they ran, because we filter out some shifts where they ran cleaning processes, because we couldn't use the data since the production was not pre-produced until the operator. Next we did convert the shifts to time-independent variables for each shift, so that we could compare shifts of different lengths, because they have different day, night, and afternoon shifts. And we kind of focus on characterizing the operator behavior instead of characterizing the result, so that you could hopefully recognize operators from the way that they're running the process. So we had 14 variables for each shift, and from that we then wanted to first run a Gaussian linear model to predict the performance of the shift.
Now we don't have anything to show, but this is some of our results. So if you imagine having like a PCA, and we took the first two components, so we wanted to do our initial data inspection. Then, how does it look? We have different colors. But yeah, we wanted to see if the variables that we chose, if some of the variants in that could explain the performance of how great a yield of isopropyl alcohol that the process gave, given the So we found that actually there was a correlation along the second principal component for this one with the performance, so the yield of the isopropyl alcohol. So during a shift, there is some kind of behavior that will actually maximize the yield in some way. So therefore, we decided on building a general linear model, Gaussian linear model, to be able to predict the performance, so to be able to find this actual behavior, but given the what's called the 14 different variables that we extracted. And yeah, what else to say? We made a model. Maybe I could draw it as well. So. Sorry. So we made what's called a generalized linear model, which is using what's called like which is producing the yield in the end. So we have for every time point, y/t, this is the performance, the yield, it's called amount of isopropyl alcohol coming out of the process. And then we have the other variables that we made at the shift t, which are the variables that we want to kind of distinguish between. We want to find how much they actually explain this performance. And this one we wanted to multiply with a slope, or b beta j. So j is which variable, so out of the 14 variables that we have. And well, so we had the multiplication here between these two. And then we also added, of course, an intercept here. And so we wanted to have some priors on this beta values. So we used what's it called, the global prior. We used the horseshoe prior. So we used the global tau for the variance here, and then single lambda for the variance for each variable. And then we also multiply these together, and they go into a normal distribution, which has zero mean, and it has tau squared times lambda j squared. And this one produces each beta j. This way it's it's gonna be sparsity inducing, so the tau is gonna pull the weights, what's called these betas, the variance to be high, and then the lambda j's are trying to actually pull them down, given this horseshoe prior here. So we had a prior on this one, and then we had another prior on this one, which was 0, and then tau 0 squared. Yeah, where we choose this one from the number of parameters that we actually want. So we had a p0, which we could, I don't know, choose to be 5 or something like that, and then calculated tau 0 to be what was it, p0 over the number of variables plus 0, and this one divided by the, it's going to be a bit messy, by the square root of the number of data points. Yeah. And in this way we chose this one. And yeah, perfect. And very soon you're going to see the model. Yeah. So these, in the end, these beta parameters, they would produce the mean for each for each output. So what?
Command option E.
What is this? So that's
Perfect. So this is our model.
nice.
Yeah. It's always good to draw things. So in the end, we would produce the means, and then we would have a global sigma for all of the different variables, and then we would draw the performance in this one. And yeah, we just divided it into all these shifts, T shift, N shifts. Yeah, we have. I think that's our model actually. So Lauren, what did our model show?
So,
Results?
fortunately, I don't have to draw all this. So this is the beta coefficients the model showed. So we can see that most of them are not relevant for the model at all, and we have the feature 1 and 5 that are very significant in their contribution. And then there's also like the index 0 and 4, which we just heard in the presentation before. They're probably collinear, so they have exactly a contrary contribution, and there's more noise to it. So that's probably out of collinearity. And if we look at the accepted samples from the lambda sample distribution, that's the one that's trying to make each of the coefficients important. So that's modeling the noise for the coefficients. You can see that those that are not important are only accepted when the noise was really low, and thus the coefficient had basically no contribution. And for 1 and 5 and 4, we can see that those were the ones with the biggest contributions, so they are probably most important. And to look deeper into that, we made a recursive feature elimination, as we see here. So that's the amount of features and how well the model predicts with that. And we can see that the most important one is number 5, which was on the one, which is shown here, down here. So that has large contribution, and you can see with 2 variables, we basically get all the predictional performance. And the question is, why is that happening with number 3? That's actually, do we see it? Yeah, so that's exactly what's happening there. So there's 2 variables that are basically contrary, and if you add the 3rd one, it's going to make the model a lot worse because it lacks its counterpart, which would equal it and neutralize it. And if you then add the 4th variable, which is then a counterpart, you basically have no effect at all. And that's like why 2 variables are basically already what we should choose to predict the performance, and has very good outcome for the prediction performance.
And they're both based on the second set point. So there are 2 variables that the operators can control, and these 2 that we add here is based on only one of them. Yeah.
Okay, so that are the results this far. So Max is going to tell a bit more about the approach from now on.
What we actually wanted to do was to model every single action that the operator performs. So a bit more in the reinforcement learning context, if we could see the operator as a player playing a game, and the game is the whole environment here. So we actually wanted to predict every single time point. So therefore we also proposed this time-dependent model that would be a next step prediction model. And it could be like we could use like a hierarchical Gaussian mixture model to find the patterns in the behavior, and we could also use like a hierarchical hidden Markov model
which is actually unsupervised because we cannot know which operator is working when. But then we could notice some patterns, and maybe we could notice which shift belongs to which operator. And in this way, we could enlighten the data and find an optimal strategy. Yeah. And in summary, so we could actually predict the performance of not every single operator, but just given some variables. So it would be possible to find an optimal strategy, or like what's called mean value should this set point have to gain the highest performance in a way. So we could actually use this to make consultant work and provide some information for the company. And what else do we have to say about this? So we got like very low squared error on the predictions, but it's of course only on the training data. We didn't do it on a validation set. So of course it becomes very good. And then we have these future plans to look at it in more detail, so in every time point. Yeah, so we can predict that.
I would also add, I didn't go into much detail, but the variables we have, for example, how often the operator shifts, or what kind of jumps he generally makes. So if we can lead that behavior back, or lead performance back to this behavior, we could then extract rules like, for example, if you shift, you should always shift in big jumps, or you shouldn't go really slow, or you should go slow, so that we could derive concrete rules for the operators to improve their performance better and faster, as they have to learn new operators. So that's a hope for that's what we hope to achieve this current one.
Yeah. So who has the first question?
Can you show the slides from the beginning, because you clearly made a lot of effort for the figures, so you can show all.
Yeah, that one is not just the process. So
yeah, this is the two set point variables,
Mm-hmm.
the upper ones, and then this is the performance variable that we have the yield. Yeah, and they're all normalized here. Yeah.
So this is our data pre-processing. So we start with data, we find the relevant parameters that the operator actually shifts. We filter outlier shifts where there's a cleaning process, and then we calculate our operator characteristic features for each shift. And so one of the important characteristics is that they're time independent, so that no matter how long the shift is, we can always get a hopefully comparable values.
And this was also one of the major ideas, one of the major changes that we made in the data was that we compressed it, into one shift. So we were looking at the overall tendency during the shift instead of every single time.
Yeah, this is just all the calculations for it, not of interest, but this is the plots that were shown, which is the PCA. On the left side, it's shown the colors are different shifts, so that's morning shift, evening shift, and night shift. So we can see that fortunately those variables are spread over all shifts, so there's not a tendency that we can say people at night don't work well. But we can see that from the first two principal components out of all those variables that, especially in the second principal component, there is like deep red means very good performance and deep blue means very low performance. So we all know that guy who really screwed up the production was probably his last day. That's why it doesn't occur often. So we can see that there's actually a signal in it that says if you play with these features, then you're going to have better prediction, which then leads to the assumption that an operator actually matters in the process, and that's why they probably want to hire educated people for it.
Instead of monkeys.
Yeah, and from then on, you saw all the plots.
Yeah.
So I have a question. I mean, is this really a reinforcement learning problem, or is it something, or is it a regression problem?
Right now, it's a regression problem. We made it into a regression problem because it was out of the scope. So to make it, it's not really well suited for Stan as well to use so many time points as we wanted to. Now we ended up with 700 shifts instead of having, how much was it? 140,000 time points. So yeah.
going to stay a regression problem because our latent plans are to predict the performance of each operator separately, so it's also a prediction. And then based on that, you could do reinforcement learning or extract rules for behavior, and that would equal to a reinforcement learning problem.
But replacing the operators, that would be another task. That would be more like a reinforcement learning.
Yeah.
Task.
No more questions?
Maxi?
Yeah. We need the. Oh. Oh, now we need to go through the whole.
Oh, yeah.
Which source was it? One. All the way back. That's nice. The other. Hvad siger du? Vi gør det der.
Alright. So what I was looking at was whether we could predict the resistant colorectal cancer. And as I told you last time, a lot of the motivation comes from the fact that this is one of the diseases which is most likely to kill you if you're a man. The survival rate is extremely low. There is multiple different treatments. People don't really know which one to pick, so the doctor usually just picks the one he feels well with. The doctor picks the one he feels most comfortable with, and it takes around 2 weeks to conduct an experiment on you as a person to see if this treatment actually works, and you do not have these 2 weeks. So what I want to see is, can we actually predict how likely it is that this treatment works on you? So what you see here is a subset of a large experiment which has been conducted across multiple types of cancer with multiple types of drugs. What you see here is the IC50 value, which is a half maximum inhibitor, basically saying how much of a certain drug do I need in order to kill half the tumor cells. It is, here we're looking at 47 different cell lines, which is equivalent to the cells that you would find in a human, across 75 different drugs. So, what did it do? One of the main problems within this field right now is that a lot of people think of this as being a binary problem, because either you get cured when you're exposed to a drug, or you don't. But as you see here, there is a huge variety within how these drugs affect your body. So what I want to do is, can we come up with some sort of regression model? Well, that was where I started. But then I started looking into some other approaches which people have been using. And some people are starting to use decompositions in order to solve this problem. It has some problems, but I'll talk about that later. So, Bayesian matrix factorization is what I decided to use. The basic idea is we can decompose some vector into two latent spaces, which is F and G, and from there reconstruct R. So as you see here, we have some priors, which people usually just set to some normal distribution with some variances that you usually pick as yourself. So from there, you come up with, you create these posterior distributions for every single variable, assuming this is a Gaussian process, from which you can come up with a likelihood so you can predict missing values. All right. The way that people usually come up with these posteriors is through Gibbs sampling. That's sort of the easy brute force method. Some people also use Bayesian inference. Apparently it works well for small problems, but as the problem increases in size, it becomes more problematic. What we wanted to do is we want to minimize the mean squared error together with some regularization of our parameter or our latent spaces, F and G. And that's what you see up here, is the mean square error that we're trying to minimize. And as you see here, it is really fast at reaching something which seems fairly well. And from there, if you look at the axis, it converges super, super slowly. This here should have been 100, but it's 3,500 iterations, and it's decreasing a tiny bit, but it's almost impossible to measure. That's why I scaled the axis as I did. But it's super slow convergence, but we're pretty fast at reaching something good. So, as you saw on the previous slide, we have to pick a dimensionality for these two vectors G and F. And as you see here, I came up with, I picked the value 4 for this K value. And here, this is the IC50 values that you saw before, which is somewhat correct. What you see here is actually the reconstruction of this decomposition I was able to perform. And as you remember, this is R is equal to G, oh sorry, F times transpose G plus some noise. And as you see here, since these are all meaning that we do not have a really high noise level within this data, so I use that as an argument to say that there is actually something with the data we're trying to capture such that these is not binary problems. And one problem with this approach, or there is multiple problems, is that here this is the feature. So with the K equals 4, we can plot all the dimensionalities in the F matrix against each other. And as you will see, since we're using this Gaussian posterior, these are all Gaussian distributions, so we can't really interpret them super efficiently. One thing which would have been super nice if we could tell which were resistance and which wasn't, but unfortunately that's not the case. So what is sort of next? You can actually use this approach to do a in-matrix prediction or out-of-matrix prediction as well, because you saw we had this likelihood function, which was also a normal distribution, which you can compute for every single one of the missing values. Unfortunately, I have not been able to make that work yet, but hopefully it will. Another thing which some people have tried and shows really, really good performance is this hybrid matrix factorization, where you factorize multiple matrices with different informations into some latent spaces. And why is this a good thing? I don't remember from my last presentation, I also have representation for every single drug, giving their number of targets, basically saying that these drugs are not identical. Because right now I just assume that they are, but I can actually prove mathematically, or I have a mathematical representation that shows that these isn't. And the same thing goes for these cell lines. I have genome sequences belonging to these cell lines. So it could be really, really interesting to see if we can decompose the IC50 values, the cell line representation and the drug representation into some latent variables, which would actually reveal which of these cell lines is most likely to be sort of well impacted by a game tree. Unfortunately, this is kind of tricky. And I've found an implementation online which might do the job. Otherwise, I'll maybe try to implement myself. So yeah, that was 7 minutes.
Okay, I have 2 questions. One was that you said that, let me ask in a different way. I mean, what kind of inference method did you use? Do you do penalized least squares, or did you do Gibbs sampling?
I used the Gibbs sampling.
Okay, then you said can also use Bayesian inference.
Yeah.
Then my question is Gibbs sampling Bayesian inference?
Is Gibbs sampling Bayesian inference?
Yeah, is it?
From a mathematical perspective, I think yes, but at some point you reach something which you can't integrate, and then it's no longer. Bayesian inference, as far as I remember.
I think the first part of your question is correct. I mean, you can show that Gibbs sampling obeys kind of detailed balance and so on. So it is like a valid market change on the carbon method. Okay, then my second question was the slide where you showed the patient features. I didn't get that at all. I got very confused there.
Oh, so basically what I did, I had this matrix F into which I decomposed the patient features. This has the dimensionality I times k, and I just wanted to plot these to see if I could find any interesting. And basically, to me, what this reveals is that I'm using a non-linguistic.
But I mean, go back one slide. This has nothing to do with patient data, right? This is like a lab experiment where you have different cell lines and drugs.
I refer to the cell lines as the patient data because that's as close as
okay.
you get.
Okay. So you kind of you visualize. Okay.
Yeah,
you visualize some kind of loading of cell lines. Yeah.
Unfortunately, you cannot conduct these experiments on patient data efficiently. Then you have to sort of grow it within.
Yeah. Sure. Oh, okay. I get it. I get it. I get it. Yeah. Any more questions? No. Okay. Thank you.
So the extension that I'm usually using to make my Jupyter notebooks a slide doesn't work with my current version of Jupyter Notebook, so it's going to be a rolling notebook, but I have hidden the code, so it shouldn't bother you too much.
Yes. Yeah. Be patient.
It's going to be a video message of our alien overlord.
That was the joke in PF technically we just made a lot of small videos with all the everyday technical issues. They are everywhere. Also with the doors. And there's like people who have this problem. Like I often have a problem with the door.
So I'm just gonna start talking. Those of you that were there at my first presentation know that I have been working with some with democratic breakdowns or democratic declines in countries, and my data consists of about 150 countries, going from the 1800s to 2010. Of course, there's a lot of missing data, and for now I've just disposed of the missing data. But it still gives me some 8,000 observations, and it is of course heavily unbalanced because most countries doesn't experience democratic decline or breakdown in a given year. Last time I talked about that usually in the literature you use just a binary indicator saying does the country break down or does it not break down. But as I also said back then, I'm not really satisfied with this approach because often the definition of breakdown is kind of arbitrary, and also I think there's a lot of difference between how bad your breakdown is. So instead I constructed a variable that just tells you from the given year how much
if any, is the country going to decline on the polytitude democratic scale the next year. And the polytitude democratic scale has 21 points, so the maximum theoretical amount of democratic points you can lose the next year is 21. No country has ever done that. The one that have lost the most was 19 points, and that's only happened one time in my data set. To fit this data, I first tried with a normal Gaussian linear model, and of course that didn't work very well because I predicted negative values as well. And of course, some countries have an increasing democracy some years, but that's not really part of my variable. Then I tried with a Poisson model and a negative binomial, and due to a problem in my data that I think I now have fixed, it didn't work at the time. So I haven't implemented these count models yet. I hope to make it work before I hand in the final report. So what I did instead was then just So I retreated to the logistic regression, to the safety and comfort of what I've done many times before. So the variable then I just made was just, do your country decline anything the next year or nothing? This is a waste of information because of course there should be a difference between a country declining only 1 point and a country declining 4 or 6 or 7. But it's what worked for now. I then implemented a couple of models. I implemented 3 models, as we also did in one of the assignments, a pooled model, a separated model, and a hierarchical model. And the idea was just then to see, as I talked about in the other presentation, how much modernization, how you should measure modernization. Can you do it just with GDP per capita, or should you also include infant mortality as a proxy for general well-being and living standard, and an interaction term between them both? So in all, I made 6 models. One which I call the full model, which has a number of variables I could show you, but at least it also includes GDP per capita, infant mortality, and an interaction term. And the other 3 models, a pooled, a separate, and a hierarchical, does not include the interaction term or the infant mortality term. And then I just ran these 6 logistic regression models. I looked at the parameter smoothing importance samplings, leave one out results. First to say all the k values were good, so I didn't have any problems there. And yeah, and it seems like for some of the models, the infant mortality variable and the interaction terms were important, but for most of the models, it actually did all right just with GDP per capita. So the problems that I'm having now, other than just the slides showing, is that I am only using a subset of my samples because, as I told you, the samples, the whole population is heavily unbalanced. And when I use the whole population, I'm greatly underestimating the chance that any country would experience a democratic decline. Of course, the chance is small, but it gets even smaller. So right now I used a balanced data set, and my models does all right. The posterior predicted distributions predict a 50-50 split, and that's the subsample that I use. So that's all right. I want to incorporate year also as in the hierarchical model, because for now I have only incorporated country. I also want, as I said, to turn back to some count model. And I would also like, I think, to model a hierarchical relationship. I have dabbled in it, but a hierarchical relationship between infant mortality and GDP per capita. because I have the same problem that Aki pointed out earlier, that of course the interaction term, but also infant mortality is rather correlated with GDP per capita, which it makes sense. It was a very, very nice plot done down.
I think you could, if you put your laptop on that counter, and then you can
yes, I will do that. So these are the problems that I'm working with right now. So this is just a bit of help. So this is just to show my data is heavily unbalanced. This is the full data set. This is all the zeros, and you can basically not see the ones. The histogram further down. Here I have removed all the non-events. So here you can see the distributions of actually democratic declines the last 200 years. Just some theory. These are the K values. They look good. We got some few one that's just hitting the 0.5 mark, but nothing above 0.7. And these are the PSISLU value and the effective parameters. Interesting perhaps that in the separate model it doesn't seem like it does not notice the interaction term and the infant mortality parameters, but it does seem to notice them in the hierarchical model. I haven't really found a way to conclude on that yet, but I think it's kind of interesting. These are the posterior predictive distributions, these are the probabilities, and these are just with a threshold of 0.5. It is not that interesting as long as I use a subset and not the full sample. And I haven't, on this slide I don't have all the convergence diagnostic, but just as we see here, the orange one is infant mortality and the low one here is the interaction term. So you see, as Aki talked about, that these are probably, they are very correlated with GDP per capita. So I think that's that. And as I mentioned last time, the reason why this is important is that there is in the literature an idea that, or not an idea, it seems that democracies don't go to war with each other. So democracies would like other countries to be democratic. And also it seems like which countries have democracy. So therefore the idea in the 90s was that if you could just make a country rich, it will become democratic and you will never have wars again. Of course, as you have noticed, it hasn't happened yet. And I must admit I have used a long time now looking at this data in various ways, and I think that if I were to actually try to predict democratic breakdown, I would definitely use some other variables than just some indicators of modernizations. I don't think it is that fruitful in the long run to focus only on these variables. So that's that.
I think the next group should start trying to set up, because now I'm getting very skeptical while we take the questions.
I also, and I don't know if any of you, other than I can perhaps have any experience with it, but in the MC stand discussion for it, it seems like that I should perhaps be using something called zero-inflated models or hurdle models. I haven't implemented those before, but if I can find the time, I'll definitely try that. Early on, there has been people have done something where they have just, like me, taking a subset of the data, which was a bit balanced. They had like 3 parts non-events and 1 part events, and then they used what they call a Bayesian correction afterwards, which was just taking using as a prior the true relationship. So no distribution, just the hard number, the amount of breakdowns that you actually saw, or declines that you actually saw during these 200 years. And this is of course not fully Bayesian, but a lot of things that's called Bayesian aren't. So I will try to implement a bit more elegant.
So if you had a zero-inflated model, would you then try to balance the data, or would you just include all of it? Right?
Yes, that would be the point, not to do this thing where I first balance the data, because I also think it's a big waste, because some countries are special or weird, do some, and I really don't want to exclude that. I tried also to make just an oversampling of the events, and it didn't work very well. First of all, when I tried to do it with all the different counts, then of course I went from 8,000 observations to 150,000 observations, which was way too big for my computer to handle and understand. So I would really like to implement a model where I don't have to undersample or oversample, and I think perhaps zero-inflated models is the way to go.
So did you have, so was it continuous or discrete?
I tried first with discrete, from 1 to theoretically 21, but then I retreated back to just 1s and 0 because due to the problem that you solved yesterday, I couldn't make posterior predictive distributions neither when I used a Poisson regression or a negative binomial. And then my conclusion was, if I can't get out posterior predictive distribution, then I don't believe in the model. So that's why I retreated to the logistic model. Yes.
And while we wait for the presentation, I'll say something about the zero inflation. The zero inflation is the wider term, but then it sometimes means also specific model, and then you mentioned hurdle. So if we have continuous data, and sometimes we see that kind of data that there's a bunch of observations exactly at 0, but then there are also observations which are clearly away from 0. And then you would make two models. One model is then predicting that probability that y is 0, given then the data, and then the other one and the other model would be then for y, but conditionally that y is larger than 0. But now it's possible to do these models independently. So here you just have data classifying whether it's 0 or non-zero. Then you have a model which just use the data conditionally that the data is larger. With discrete models, there's a difference that you have counts 0, 1, 2, 3, and so on. If we assume that we have more, we would have like Poisson model, and Poisson model itself would have then something like this. But if we now observe here more, we say that, okay, yeah, there's a zero inflation, but then there's two options we can do. This one approach would be called then the hurdle model, so that you would have again a model just saying that what's the probability that 0, but in a hurdle model, this part would not be the Poisson or negative binomial, but it would be terror truncated, because you have the condition that the count has to be larger than 0. But then you can modify Poisson or negative binomial model so that this one tells the probability of this, and the other part tells only the probability for these, but not this one. But then there's also the zero-inflated Poisson and zero-inflated negative binomial model, which is then a mid-term. So that we have then alpha times b y equals 0 part, and then plus 1 minus alpha, and then the y now we don't have the restriction that it has to be larger than 0. And then so this would be then the plus 1 and negative binomial. So it's then
the hurdle name comes from that in the way that there's some latest process which says that in the way that we have to first go over hurdle before we get these non-zeros. There are some cases where we might be able to kind of really identify also which one is better. Of course, if the probability from the plus or negative binomial of 0 is very small, then the hurdle model is enough. Hurdle model is easier because you can do two different models separately. And then that's why I would recommend first trying hurdle model. But there are cases where then the zero inflated works better.
Thanks.
Oh, I have a few comments. I mean, about the balancing. I mean, this is not in the STAN context, but in the general context, what I recommend is to actually use all the data, but then as your metric, use the area under the curve, right? Because area under the curve simply measures whether you are actually able to put the right candidates first. So that was my first comment.
I implemented that, but I don't have it in the slides.
So it might be that it always predicts everything will stay the same. But if you look at the kind of the cases it identifies as being in the danger zone, it might find the right ones. My second thing was a question: do you look at prediction? Are you building a predictive model? I mean, are you holding out data and then predicting what will happen next year, or are you only looking at the training data? So to speak?
No. The idea is right now I was only using the PSISLU, but the idea is definitely to exclude some years, the later years, and then try to predict them and see how good do I predict the next year and the next year after that and so forth.
Yeah.
And ideally, then you would make some kind of survival model. I'm not gonna do this time because I don't have the time, but that would be, I think, the right way to do it.
It's probably very non-stationary, but
yeah.
But I mean, I think it's nice to formulate it as like a 1 year ahead prediction task. Of course, you have to run many models then, but then it's much more realistic, right?
Yes.
For what you ultimately want to use it for is to say, okay, will this country now turn sour next year?
Exactly. And that's also how I constructed the Y variable. That is constructed so it is, how much are we gonna decline next year?
Yeah. Good.
Thank
you.
So to recap on what we proposed to look at, so we were looking at clinical trials, patient selection within these clinical trials. So if you don't know, a clinical trial process takes around 10 years. It costs somewhere around $600 million. And it's broken up into phases, in which each phase can have up to a 50% chance of failure, costing the pharmaceutical company a lot of money. So their aim is to optimize this process and find a way of selecting patients which will respond to the treatments, so the treatment will be effective. What we're working with is data from a clinical trial, in which patients have had various different biomarkers measured, which are tissue-specific, which is supposed to represent the underlying disease that they had, which was rheumatoid arthritis. And the aim of this is to use these biomarkers to predict, before they start to take any treatment, if they will respond to the drug, so we can remove them from the clinical trial that day. We had 5 biomarkers that we looked at, which you can see here. About 20% of the patients that we actually looked at responded to the treatment in our data set, so another unbalanced problem. It was also the case that a lot of the... So I'll show the distributions first. So this is just some exploratory data analysis with the biomarkers we had. in which the distributions, as you can see, very much overlap, which is the case for all of them, in fact. Some potential outliers, even though these are claimed to be true values. And they also follow somewhat a log normal distribution. So that the claim from the company who develops these markers is that we are able to separate between these patients who respond and patients who don't, given that may be slightly skeptical. So that was what we aimed to do, was to identify if this was true. So here we go.
So as you have said, we have selected 5 biomarkers based on the disease we are studying, which is rheumatoid arthritis. And we have selected markers that show us if there's an inflammatory response because and bone degradation, because it's a disease where I guess that we all have seen our grandma with arthritis, and we have a degradation of the bone and inflammation. So we want to see if in blood we are detecting those molecules that are showing us that something is happening in the bone. So based on that, we have selected those biomarkers. We just now focus on the names. And the first we have done, we have modeled this as a case of a log normal distribution with known mean and a known location, a known variance, sorry. So this is the code. And for each biomarker we have plot, and we have done using a weekly informative prior. We have plotted the difference on means, and we have computed the probability that the means are different from, to 0. And in some cases they are centered on 0 or close to 0, but we get some quite interesting biomarkers if you look at BICOM and PIN, right, where we see that the probability that the mean is smaller than 0, it's 1. Let's say 0, it's bigger than 0.99.
So we wanted to then, even though some of these biomarkers didn't seem to be very informative, we wanted to include them together in a multivariate logistic regression. So first we started by using a student T prime to model this with 5 degrees of freedom on our alpha and beta primes with a zero mean and 2.5 standard deviation. So when we compile this model in SNAM, we can see that these are the weights and the intercepts, which again, as we saw from univariate modeling, BICOM seems to have the largest weights, even though the confidence interval seems to be much larger. And looking at, we haven't shown them that the diagnostics of this convergence was all good, all the chains converged. We can also see that this ELPD loop, so the number of K values below 0 was all of them except for 1. And the one that was above was at 0.63, which you can see here, which means that the model is somewhat reliable, except for this one, which is about which potentially reliable.
Yeah, then we have done the same logistic regression problem, changing the priors. So we have, even though this is wrong, we have used a Cauchy prior, which is an informative prior too, for our problem. It's the same model, we just have changed the priors. So we see that the number of efficient samples and the chains have converged. Again, the thing we see, and we don't know very well how to interpret it, is that the BICOM biomarker, which is the stronger one, now it has shifted. So if you can help us on this, that would be great. We are looking forward for suggestions. And we see that the Pareto values and the max Pareto values are relatively fine. And that the ELPD difference is fine.
There's no difference between the models. This could mean that both models are really bad or really good, we don't know. So we now have to do some model evaluation to see if we can actually predict which of these patients will go into remission or not. Since these trials are also carried out over 52 weeks, we have measurements at various different time points. So the extension of this, which we aim to do in the report, is then to model these time points hierarchically, to somehow empirically model the change of the biomarker level to see if patients are actually responding. We also excluded other variables that we had, such as demographics, age, BMI, previous number of drugs they've had, and the gender, which could be confounders, which may improve the model, although it doesn't help the biomarker development company say the biomarkers are working.
That's it.
So you could use compared to null model without no coverage, whether these coverage have any predictive relevance. So that was the. Can you solve the code for the second model based on your plots? The sign of this one parameter switched. It was
so actually these are not being used. It's just when they're normal, we just need to stay. This should be used with caution.
There must be a sign somewhere, because it seems like you had.
Yeah.
And then the first model. And priors were in this case
0 and 2.5.
What is this y equal to y minus 1 times minus 1?
So that is flipping the ones and zeros.
But you are not flipping them here.
No.
Yes, you give me self-confidence.
Okay.
Any more questions? Thank you. I think now you cured the projector, so we have high hopes for the next one.
You can just look at people's style, whether they have a Mac or not.
Don't touch anything.
It was first when I came here to GTU, I was kind of accepted. It was okay. But in physics, it was really
Yeah, I think the problem last time was that the resolution was
it was more like do it yourself. People were like,
but Windows was okay.
Yeah, I think that's it was more that it's like, oh, it's fancy. It's like, we're not fancy here. Here we just practical. Like,
were you allowed to use Linux without only to command line?
I think because Windows is more the default choice, so you can't really hit someone for being average, but make it bad.
Yeah.
Yes, you have to make a conscious choice.
Nothing. Just flip the cable.
So that's why you get hit. Yeah.
And especially in data science, doesn't make sense. Because Windows is the biggest garbage for all the backslash, double backslashes that you need in have systems, and it's just like Unix and everything like Unix.
Yeah, but it works.
All right, fantastic.
Works, yeah.
Yeah, so we were modeling the basketball games in women's college NBA March Madness. I'm Maxim, and this is Saita. So our data is basically 64 teams who qualified towards the tournaments, as you might remember. We are to predict the outcomes of each match, and we are to predict the number of goals in for each match as well. We thought that could be interesting to model as an additional problem. And then we have one data set which is compact, that's from '97. And then we have another data set from 2014. And let's show how it looks like. This is the compact data. This is the one where we have the longest time series, longest number of matches. It's fairly rudimentary. The winning score, the losing score, whether or not they're on the home court, whether or not they're on the away court. Now the detailed data is that, and in addition to that, we have the number of field goals made, the number of three-pointers, attempts of three-pointers, attempts of field goals, number of steals, blocks, whatever you could imagine. Now,
yeah. So let's just start with what has been done before on this kind of problem. So when we were searching for this whole literature thing about what has been done, and people have mostly worked on football outcomes, and nothing specifically has been done for basketball or any other sports per se. Maybe it's because more money is involved in football, I don't know. But so what people have done is the popular approach has been using a Bayesian distribution to estimate the number of goals in a match. But this assumption is questionable because it has been shown that there is a problem of over dispersion, where your standard deviation is much higher than the mean. And also the empirical evidence shows that there is a slight correlation between the goals in a game. So for example, if a team scores first, and so it kind of boosts your morale, and it's shown that the leading team will have much higher probability of scoring another goal. So these are kind of the intricacies of this kind of approaches. And Maher discussed this issue about correlation among the goals in a match. And Dixon in 1997, they extended an independent Poisson model and of course incorporating a type of dependence into it. And then there was a recent approach which uses Scalam distribution to kind of model the goal difference, and they claim that this gets rid of the correlation because two teams are competing against each other. And of course the assumption of the distribution of the goals being Poisson need not be considered here, so it's kind of a stronger model. That's what they claim. So what we have done is we have two models that we have built, and a Bernoulli GLM for modeling the outcome of a match, and a hierarchical Bayesian Poisson for modeling the goals scored in each of the match by each of the teams. So up to you.
Yeah. So start out simple. Let's do a logistical regression with a somewhat informative prior with two student T distributed parameters, namely the alpha and the beta, where alpha is the intercept and beta is each of the features in the data set, how many goals, how many scores, and whatnot. And by doing this, we found a decent fit. We see that there's a pretty good convergence. The beta distributed parameters do seem to have some difference and code for something interesting related to the match. And we also see on the individual Markov chain iterations that they do center around certain values, do not diverge too much. This is also apparent when we look at our diagnostic values. We generally have a good N efficiency sample, and we have all our R hat values that are within an acceptable range. Yeah, and we have no estimates that are above 0.5 on the Pareto scale. So if we look at the marginals, this is what the odds look like in relation to whether or not a match is won. Based on what we've heard earlier today, there might be some collinearity issues in the different distributions. What you're seeing here is a difference between each of the actual parameters. From the top, you have the score and the field goal made, and the free throws, the difference between the two teams in each match. And well, if we were to take these results as given, you'd see that the number of field goals, three-pointers made is significant towards whether or not you win the match, which sort of makes sense. What makes little or less sense is the fact that the actual seeding does not seem to have an apparent big relationship towards whether or not the match is won, and as well as the score difference. So there might be some tweaks and some works in this particular model that requires to be improved.
Okay, so now the second model is the hierarchical Bayesian model. So the motivation for this is we just wanted to see whether the claims made by everybody that Bayesian is the best one to model the football outcome is true or not. So we kind of plotted an empirical histogram of the claims we had for 20 years. And the distribution you see on the top is the outcome of 1400 matches from 1997 onwards in the basketball. And we found the mean, and with the same mean we simulated the Poisson, and we could see it's may not be exactly same, but we can maybe do it with the Poisson. So that was the first starting point, and finally this is our actual model that we are. So the goals you see are divided into home and away. So before I start this model, I should say that I have discarded those matches which are played in a neutral venue. So this is specifically done on like a home and away from a football perspective. So the parameter lambda, which we are trying to estimate, is it's made up of three more parameters, which is baseline, which is kind of a home advantage or away advantage that you could interpret that. Skill I and skill J are the skills of two competing teams, and each of them comes from a distribution, and we have given the priors. Because I have no clue about basketball as much as such, so I have chosen some random priors to see whether it works for now. And of course, this is the basic model, and in the baseline, I have divided the baseline into home baseline and away baseline. So the intuition was when you are playing in home, so you have a much higher chance or higher modal boost, kind of the intuition is. And all right, and the assumption is each of the team has the same probability of making a goal when given you have equal goal chances. So having said all this, so let's see the posterior. So this is the posterior of home baseline and away baseline that you could see, and the top one is the home baseline, and you could see it's slightly higher on a log scale than the away baseline, and which kinds of confirms our suspicion that you have a higher advantage when play at home. And how does it interpret in the results? So this is what we have done, kind of just to make interpretation of this thing. So I have taken an exponentiation of the home baseline and away baseline, and I subtracted it just to be able to show how much points it affects in the match. So you could see there is a clear home advantage. So if you're playing at home, then you have a higher chance, or maybe a mean chance, of scoring 8 more points. That's the kind of intuition we have. And also we plotted the posterior of the skill parameters, and we have ranked them based on the, this is the top 40 teams, and we had actually 216 teams throughout 20 years who made it to the top 64, in some years who didn't make it. So from this, you can do a ranking based on the posterior you have. And our conclusion is, these are the top 3 skilled teams throughout the last 20 years, and the least skilled teams throughout the last 20 years. And also we need to verify this because we haven't done a predictive checking yet, so we should be able to do it in the next few days.
So all the finals have been played for 2018. Last game was on April 2nd. So,
but that was a neutral game, so
sure. But yeah,
so we need to.
For the outcome, at least we can check.
Yeah. So what we are planning to do in the next few days before we submit the notebook is play around with hyperparameters and the priors to get a better estimate of the outcomes, and to find a way to do a model comparison between the 2 models and do some posterior predictive checking. That's the whole idea. Thanks.
Can you show the previous, this one, yeah. So this is very good. They show the uncertainty in a way that how difficult it is to. I mean, there are a couple teams which are clearly better,
yeah.
But for most, it's really difficult to say that what's their rank,
yeah.
and even.
But there's unfortunately a caveat in this, because more than half of the matches are played on neutral ground. So we had to discard quite a bit of data in order to do the actual away or home.
But I mean, it's also that it's really common when comparing anything. This is usually so for example in UK they are comparing hospitals, and then in many countries comparison of schools and so on, and then just making a ranking list and assuming that there's no variation from year to year just by chance. And then also looking at the kind of the changes in the ranking from year to another year, and if the kind of the criteria used to rank is noisy. So it would be better always to show these kind of uncertainties, and quite often it would be better not to even make a ranking list with specific numbers. It's also possible then from if these are the skill parameters, you could sample from the posterior of skill parameters, compute ranks, and redo, and then you would get the posterior for ranks, and you could also, if you want to make a ranking list, you could show that, okay, even the worst team is likely to be somewhere from the worst to middle.
Mm-hmm.
What is the overall goal with this model?
There are 2 goals. One of which is predict the outcome of the match. That's the logistical regression model.
Yeah.
And then this one is to see whether or not there's a proven difference between whether or not you play on home court or an away court over time within each team.
So the setup with predicting the outcome of the match, then all your covariates, that's kind of based on previous matches, I guess.
That's true.
Yes. Okay.
For
It took me a little bit of time to
yeah,
figure that out. I couldn't understand why score difference didn't determine who would win. Yeah, okay, I get it.
And I guess you don't have that data, but the additional things. Additional things would be if you would have a number of how many of the people in the audience were from which team, because I know at least in I think in like Premier League football, they have also reports on how many of the home team audience there was,
yeah.
and then
Okay.
away team audience. In a way that when you are playing in a neutral, or even if you are playing away, but you are playing somewhere so near that there's a lot of your team fans also coming there. So is the kind of the, is it important the place where you play, or is it important how many fans you have?
Yeah, that's a good question.
Because there have been experiments also, for example, that of course the noise fans made raise your spirit, but it's also in football, it affects referee results.
Okay, yeah.
Because they've showed videos of events without any sound, and with the sound of the audience there for experienced referees, and they made a different kind of decisions based on whether they hear the sound or not. And so it affects also referees. And then the other one, the kind of how the place actually can affect is that it's your 3D orientation, that in a way that how do you know where the goal is based on what you see around, and if you are in a different stadium, you need a little bit more time to kind of orient where the goal is.
Yeah, you see, we would love to augment this. The fact is, you find some data sets and then they're only for one season, or there are a lot of missing values, or they're payable. But it's a very interesting question. They must have an entrance with each fans, perhaps, going into a particular entrance, maybe logging that. Yeah. It's,
How do you plan to make this model kind of time dependent?
for now, we don't model the temporal resolution.
No, but I mean, of course, to make it any practical predicted value, it doesn't matter how my team played 20 years ago if they suck today, right? But that's in your model, you pool everything.
We did, yes.
Yeah.
But that's a to-do. That's on the to-do list.
Good.
The temporal resolution would be very, very relevant to get into this.
But for example,
we don't know which teams partake in each season, right? Well, we know which one will partake in this season, but
how
we
could
don't
you?
know which matches they get linked? Which teams get linked to each other in each match.
But could you? Okay, so just very quick last question. Could you set up an experiment to kind of determine whether it's necessary to have temporal modeling?
There has been a paper that I was reading that they have, I mean, it was a winner of a competition that have done this. So they took this skill as a temporal variation of the season. So there is like an autoregressive kind of so your skill from last year is a variable from skill of this year plus some alpha or beta based on some historical data. But they claim that it didn't change the model much, but it made more sense. But
good, thank you. Are we done for today? Yes, we're done for today. So it's sticker time, I guess.
Yeah.